So far, while performing Laplace transformations of functions, we have noticed that by assumption, this variable here of the transformed function f of s, the variable s is assumed to be real. But this doesn't always need to be the case. It might be convenient for us in many instances for considering s to be complex. So let me talk about one of those instances where we can find it handy for us for s to be complex. Specifically, we want to apply a result that we have already proven, that is the Laplace transformation of this function e to the power at, where a is some constant number, is given by 1 over s minus a. Alright? So what we are going to do is that we're going to use this particular transform, and along with the properties we have just studied in the last video, we'll try to extrapolate the Laplace transformation of functions which can be written as an exponential or a combination of exponentials. For example, the functions sine of omega t, cosine of omega t, so basically the sinusoidal functions, and also, for example, sine hyperbolic of omega t, and then cos hyperbolic of omega t, etc., which can be written as a combination of exponentials in a straightforward manner. So the first one we are going to do is to write this Laplace transformation a bit differently, and that is to find out the Laplace transformation of e to the power I times a t. Okay? Now, unlike the previous case, instead of real a, we have this imaginary I times a, where a is of course still a real number. And if we extend this result here to this case here, then of course we can straightforwardly write it as 1 over s minus ia. Now, of course, we can treat it to make it a bit better in appearance, and the easiest way to do it is to multiply the numerator and the denominator by the same number, which is s plus ia. The benefit of that is that the denominator becomes an interesting pattern, which is s plus ia times s minus ia. And of course, we know this thing at the bottom gives us s squared minus I squared a squared, which means plus a squared. On the top, we have s plus ia. This is a complex number which can be written as s divided by s squared plus a squared, then plus I, the imaginary unit, times a divided by s squared plus a squared. Now, of course, the left-hand side here, this can be divided into the real part and an imaginary part as well. So we can write Laplace transformation of e to the power at is basically, according to Euler's formula, cosine of at plus I sine of at. Okay? And by the law of linearity, we can write it as Laplace transformation of cosine of at and then plus I times Laplace transformation of sine of at. When we do that, of course, the real part here should resemble or be equated to the real parts in here, and the imaginary parts here should be equated to the imaginary part there. So finally, we end up with these results. The Laplace transformation of cosine of AT is given by s divided by s squared plus a squared, and the Laplace transformation of sine of AT can be written as a divided by s squared plus a squared. These results could be found by employing the method of brute force calculation and would arrive exactly at the same result. So this method right here, and an assumption which can be proven that the quantity on the output can be complex, specifically S, that allowed us to generalize this, and as a result we could have substituted I times A instead of A, giving us a shortcut to a rather complicated result. Now let us go to find out the Laplace transformation of the hyperbolic trigonometric functions, such as sine hyperbolic and cosine hyperbolic. Okay, so how do we find the Laplace transformation of sine hyperbolic? Well, this is what we are going to do. The first method is, of course, to employ direct integration results, but as you can understand, this is going to be quite tedious. So this is what we are going to do. We know the Laplace transformation of e to the power at is given by 1 over s minus a. Okay, but sine hyperbolic of at is going to be equal to e to the power at, and then minus e to the power minus at divided by 2. So if we substitute that, what do we end up with? We end up with half, and then Laplace transformation of e to the power at, and then minus half. So I can just put in a brackets here and write Laplace transformation of e to the power minus at. And what this does is to write down the Laplace transformations of these two functions directly. So the first one is, of course, via this formula, which is simply 1 over s minus a, and the second one is the same except for a is substituted by minus a, so we have minus 1 over s plus a, and guess what it is going to do for us? So we have half, and then we have s squared minus a squared. In the upstairs we're going to have s plus a minus s minus a, right? Or plus a. I think this is a plus a, right? Yeah, because two negative signs make it positive. So we have 2a divided by 2 into s squared minus a squared, and that gives us a divided by s squared minus a squared. So therefore the Laplace transformation of sine hyperbolic of at is equal to a divided by s squared minus a squared. So what about the Laplace transformation of cosine hyperbolic or cosh hyperbolic of at? Well, we have 1/2 and then L e to the power at, and then we're going to have plus L e to the power minus at. So the difference is a plus sign instead of a minus sign, because we know cos hyperbolic at, or cosh at, is equal to e to the power at plus e to the power minus at divided by 2. And of course this is from the definition of cosh hyperbolic. As you can assume, it follows the same way except for a plus sign instead of a minus. And then finally we have instead of a divided by a squared minus a squared, we have s divided by s squared minus a squared. And that is an amazingly shortcut way to find out the Laplace transformation of two important functions, which is sine hyperbolic and cos hyperbolic.